you get used to different people's writing styles and presentation styles. So you can recognize who wrote a paper by presentation techniques. Even, like how they lay out figures in LaTeX.
Oh yeah?
Yeah.
I haven't read enough papers to get that far.
Yeah.
Usually I would.
I mean, the lecture has already started, right? So you can.
Well, I guess this is true. This is. Okay. We now again have supermajority, which is a bare majority of attendees versus presenter. We'll only ever have 8 audience members who are me. But yeah, so I don't know if you read this portion like in detail or not, but
Not in detail.
yeah. Well, one of the things that I think is useful going into this is to get a picture on this figure from that supplementary reading that I posted, to see just what an exploit is and what it requires, right?
So I kind of couldn't, I know what a spatial error is, and then the temporal error I couldn't understand what is.
Oh, I don't remember how they classified the temporal error stuff.
So they say that if you come into a out of bound, then it's a spatial error. If you run into a dangling pointer, like dereferencing a dangling pointer.
Oh, okay,
then it's
right. So the issue there is that it's a question of timing, right? So if you access an out of bounds pointer, that is an error guaranteed, right?
Yes.
That is just period an error. Whether or not you're accessing a dangling pointer depends on the order of events. If it depends on order, it's temporal.
Okay. And
Right? So you have a deallocate and then an access or something like that. And, or yes, essentially something along those lines. So the order of events matters, and that's what a temporal error is. But essentially, what this diagram gives you, if for those of you who might have read the first, or read the supplementary material, like there's one section there that said, hey, this is good to read. This is a summary of how attacks are structured. There are only a few basic patterns for the structure of an attack to take control of a program. What it boils down to is that you want to get control of some kind of pointer, because if you can take control of a pointer and have the program jump to that address, then you can make the program do whatever you want, right? So the question is, how can you choose what the contents of a pointer actually are, and how can you force the program to jump to that address? And there are only a few ways to do that. One of these ways is a buffer overflow, right? Because the return address is a pointer on the stack that you will jump to. And there are just a few other ways outlined in this paper as well. There are things like deallocation and whatnot that can feed into this. So I'm not sure, how many people looked at the supplementary? Okay, that's more than I was maybe guessing.
The paper was 50 pages.
That's why I said only look at the very first part, and really, this figure is the key.
Yeah.
This figure is the best part of that paper, I think. Because it boils down the essence of what an attack is. And so if you understand this, then you start to understand how you can make an attack and what you have to constrain in order to prevent an attack. Because if you break any one of those links, then you prevent an attack along that path. And we'll look at that a little bit later on in the code pointer integrity paper.
so my question is that once a user gets access to the shell code, he can execute, I think, any command on the system.
That's the idea? Yeah, so shell code is basically an attacker program. Sometimes it'll actually launch a shell like bash. Sometimes it'll be a custom program written in binary. It could be anything. It's just a program of the attacker's creation. But if you follow one of these paths, for instance, so make a pointer go out of bounds, right? So that's where we see buffer overflow. That's like one of the first steps you can do. You can make a pointer go out of bounds, and then end up, I guess, writing over that pointer, modifying it so that it points to your preferred location of code, and then jumping to that is one example of a workflow through this system. But there are several different workflows. If you're interested in security, go back and read this. Even just this first section. Anyway, so I've taken up too much of your time.
So, hi, I'm Nivedhan, and I'm going to present automatic exploits generation. It was a paper published in 2011. So, the gist of the paper is that you feed in the program to this, you feed in a program, subject program, to automatic exploit generation, and then it gives you the vulnerability as well as how to exploit that vulnerability. So, what are the vulnerabilities which we are looking at? So basically, there are two vulnerabilities which have been highlighted in this paper. One of them is buffer overflows, or you can say out-of-bound writes, which are spatial errors. So what do I mean by spatial errors? So whenever a buffer gets overflowed, it leverages the memory space which has been allocated to the buffer. So once that buffer overflows, the excess amounts of space which I get, I can get a pointer to that and redirect it towards my code. We'll see a detailed example of that. What is unsafe formatting strings? So there's a small example up there which shows that if there's a user input variable which a printf statement is taking, you can give it something like %3 $x, which would pick up the third integer on the stack. So there's this code which has been taken from iwconfig, which is a tool, I guess, and it shows us a vulnerability which was mentioned earlier. So there's an argument which is being taken from the user, which is argv1, and it feeds into, it gets its value transferred to if name, and later on we see that it goes back to this method where an strcpy is the string is getting copied into this variable, but that if name has been taken from the user input. So a user can potentially give it any length, and that would cause a buffer overflow. So let's see that how that works. So this is the memory layout of how things are happening, and that is the buffer allocated to this variable up here. So when a user gets the input, this particular section should be the section which should be filled, and so there's your user input. Ideally, it should behave like that. But what would happen if the user gives it an input which is like too big for the buffer to handle? It would overwrite over the local space, but then if it is even bigger than that, it can even write up to your return address. What would happen there in the return address is that this is just the part where the vulnerability has not been hit yet. But the vulnerability, like the exploit, has not been hit yet. This is just the buffer being overflowed. But once the input is too large, you can actually take over the space which was meant for return address and replace it with a shellcode. So once that return address comes back to the program flow, your shellcode would execute and this program would be exploited. So before 2011, the paper claims that the normal way of solving these problems was to think hard about them and come up with a solution. In their actual presentation on YouTube, they also mentioned that there were students whom they gave this problem to students to figure out an exploit, and they took more than 4 hours, or more than half, or a very good person who would is an expert in the field would at least take half an hour with some hints to actually get that exploit. But with AEG, you can, later on we'll see that you can do this in just 4 hours with 12 to 13 softwares and explore like 16 exploits with it. So how they break their problem domain is that there are all the inputs which the program can take. Then there are some set of inputs which would have that problem where the buffer would overflow, but the buffer may not overflow such that it could be exploited. So then there are a small set of inputs which would result in a control hijack. There would be inputs which would be large enough that you can actually get control of the program to misbehave. So that is what the condition up there says, that the length of the input, if it is too large as compared to the input which we took earlier, then, and the predicate that, and if my shell code would be executable along with that condition, then that is this area which AEG would be targeting. So by this we get a feel that there were a lot of inputs, and we have successfully managed, like if this happens, we will successfully manage and take a small set of inputs which will be targeted. We won't have to like go through all the programs with all the inputs. So basically we are trying to narrowing down our problem. So the goal of AEG is to take a program and generate exploits. So how they do it is they break it down into 2 sections where there is vulnerability discovery, and the second section is exploit the generation. Like whatever vulnerability you have detected, now you can exploit it. So how they do it is, first we'll take a normal approach with symbolic execution of the source code to detect where our buffer overflows are, those variables which might be affected with buffer overflows. So discover the buggy predicate. So if we look at this example up here, X is an input which is being taken by the user from the user, and if you look at the if condition up here, it would follow the true path because it can see up there that a buffer is being allocated to X. But since it is a symbolic execution, we are not sure whether it's gonna follow this same path. It will take this path as well, this path, this path. So basically it's following a lot of paths up there. So it will be slow to find these bugs. Let's look at this example up here, and what it essentially shows is that strcpy, that particular function, what it does in detail up here. So it's checking for each and every character, whether like it's copying each and every character, and at the end, when the loop is over, at the last place, this should be a null character, I guess. So this is ending that particular string up there, saying that the string has finished copying. So in traditional symbolic execution, what would happen is that it would check each and every path, and along that path, I'm not sure why they mentioned 20 minutes and 30 minutes up there.
So because you're exploring all of these different paths, you might start off by saying, well, I could take either the true branch or the false branch, and you might explore the false branch first. And if you do that, then you could spend 20 minutes just exploring the paths on the false branch.
But according to the example, it shouldn't take this much time, because
How so?
Because in the example, it seems pretty simple that if the false branch is taken, it will just go back.
Okay, well, what happens here though is that the false branch, you can go down that, you exit the loop, and then you have to execute the rest of the program. And so there's symbolic execution for all the paths that start off by taking that false branch first, and then execute the rest of the program. And then you have to go back and say, well, what if I took the true branch? And what are all the paths through the rest of the program taking the true branch? And explore all of those. So there's a lot of complexity here. Do people see that you are exploring a lot of paths through either side? Okay. And what they're saying essentially is that maybe we just don't care about the false branch at all,
Yes.
and so those 20 minutes are wasted.
So this is an existing technique which has been implemented in Clee,
Which is also open source.
which is also.
That's so.
So what we are doing here is
But,
we are.
Helga, this automatic exploit generation, they haven't open sourced it.
I don't think that. Well,
But the tool is online.
some of it certainly is. I'm not sure if all of it is.
I tried to search for it, like, but I found the website
Yeah, yeah,
for this paper, but I wasn't able to find actual tool.
yeah,
Oh,
yeah.
really? But there was a demo how to use that tool.
There was a
There
demo,
was a
there was
video,
no
yeah.
tool, there was no tool.
That's a good sales pitch. So I'm not sure if they released. I think they certainly probably wouldn't have released the entire tool. I know that other parts of their infrastructure are released. Maybe not the parts that they presented in this paper.
Otherwise, could be money printing machine. You take this money for bug program and then you application.
Well, I would look at it this way. There could be ethical issues involved with releasing the tool in general. And so-
Yeah, totally.
So it's probably one of the things where you'd have to be a reputable researcher and request a copy of the tool.
Oh.
Because otherwise, Joe Schmo, can come along and download this tool and say, hey, suddenly I've got, 1,000 zero-day exploits. Let's make some money. Yeah, just like you're saying. That's probably not an ethical strategy.
You can he's changing his name to Joe Schmo.
I mean, like, I know companies like Google, Facebook, they actually will pay you for the bug.
This is true. This is
Seems
true.
like a business plan.
Oh, there are absolutely people who are paid to be white hat hackers to go and find exploits in, Google software and so forth. The issue is that they can't necessarily make this tool publicly available. They could consult for a company and use it. There are a lot of researchers who do that sort of thing.
So far, what I've seen is that they patented that idea. So,
Yeah, yeah.
Didn't they patent the idea?
they have patent on it, yeah.
Patent.
I'm not a big fan of software patents. I'm not entirely sure that they're even legal. But I would argue they're not. But yeah, it's definitely something that has strong chances for real world financial impact.
I will approach, I want to explore your tool. Okay, that's it.
So what we are seeing here is a traditional symbolic execution. What they propose is a preconditioned symbolic execution where there are some preconditions based on which we'll follow the paths. So we get a basic idea that we are not going to follow all the paths to make it faster. So back to the earlier diagram up here. So what they mention is that if we put all those preconditions to our symbolic execution, we'll be exploring only this area. How we are going to do that is, if we put a length condition up there, that if the input is greater than n, which is the size of the smallest buffer, in the paper they mention that it's the 10% of the largest buffer, and here it's a little confusing.
Yeah. So comments on that?
Comments on what?
So the size of the buffer. Here they mention that it's the size of the smallest buffer, and in the paper they mention that it's the 10% of the size of the largest buffer, or 10% more.
10% more than
Yeah,
the
10%
buffer
more.
size. Well, that would give you access to that would force a buffer overflow.
Yes.
thing. So is there only way I didn't look at the supplementary information. Is the only way to get the pointer through buffer overflow attacks for the most part?
So this paper focuses at or focuses on stack buffer overflows
Mhm.
and those format string exploits, which are well established.
Yeah.
There are other ways,
To gain control.
yeah, which that other paper
Mm-hmm.
that I pointed out
Yeah,
as
thanks.
supplementary material, yeah, the diagram goes through that really well. The rest of that paper is just an encyclopedia of how to do that,
Oh.
different ways of doing that.
So with that precondition, so this was the part where I was confused. So in the paper, they were mentioned that we have a length precondition up there,
Mhm.
which would say that if all the elements except for the last element is not null,
Mhm.
then then explore this path.
Mhm.
Otherwise, don't explore this path. So, is this the same thing which they are doing up there?
Yes.
But the condition up here says that if the first character is equal to null, and which is a little contradictory.
So along the false branch, there is a contradiction. They're creating a contradiction along the path they don't want to explore.
So this corresponds to that unsatisfiable path.
So yes, yeah.
Okay, then it was just spatially written.
So if you look at it, right, length greater than n, and essentially length equals 0, are contradictory. So yes, yeah.
All right. So they've imposed. Is this clear?
Maybe it would be good to work through what it's doing and then ask if it's clear.
Okay. So what it does is that this is the symbolic execution tree of that strcpy function, which we saw earlier. So what it checks is it checks each and every element to be not equal to null, and then takes the true path, and that is where we want to go, because we don't want a buffer which is of lesser length than what we have initially decided. So what happens is that every character is checked whether it is not null, and for the unsatisfiable condition, what we do is we give this predicate to that symbolic execution condition up there, that the length input should be greater than n, and this is double equal to 0. If this is the case, then don't follow that path.
So where does the length of input greater than n come from?
From the user.
Not quite.
It's mentioned in the it's the length condition.
Right. It is the preconditioning. So all they're doing is concatenating your preconditioning formula along with the constraints from the program itself. And so that preconditioning formula saying the input must be at least this big tells us that the branch is unsatisfiable.
And the precondition is user input.
I would separate this between user input and attacker inputs. It is an input for the attack derivation program, not for the underlying program being attacked.
Oh, yes, yeah. It's an input for AEG.
Yes.
Yeah. Exploitation.
Should I move on from this one?
Yeah.
Alright. So how do we select the length? Exactly the question. So the lightweight static analysis, use the size of the So their second insight is not all paths are equally likely to be exploitable. So even in those paths which we are still following from the preconditions, we don't want to follow, we want to follow those paths in a certain order where they have a certain priority. So we'll be following the buggy paths first, and so even in that path, we want to follow those paths which have seen the bugs earlier. which parts have already detected a bug up there, so that
You hear that?
We're just trying to prevent somebody from exploiting something.
So, so on the path where we would find a bug, that is the path we would prioritize higher when we are trying to exploit that particular bug. Is that clear? Why we are doing that?
I don't think you've
Explained it.
yeah, that you've explained why we are doing that.
So, through their heuristic analysis, they saw that all those paths which earlier had a bug on them, they are likely to be exploited. Say if there is a bug where that particular buffer has been exceeded by just one space, it's still a bug because there was a buffer overflow there, but you cannot ideally exploit it. But what they are saying here is that if you follow down that same path and like prioritize it higher to other buggy paths, then you can later on maybe that same particular input has been used in such a manner that it has been exploited later on.
Why might that be true?
Because people tend to use same buffers later on.
Okay, I mean, that's true in general though. I mean, so along any path, if I use a buffer in one place, I might use that same buffer later. So what does that have to do with it being buggy? This could be a question for anybody.
What's a programmer that makes small bugs might think larger bugs later on?
Sure, that's the hypothesis.
They say that they experienced it in a lot of programs, that's why they took this approach.
Well, they gave this as a reasoned heuristic, where they said that if a programmer makes a small bug and it's not exploitable, that's at least an indicator that the program who wrote that didn't know what they were doing, and is likely to make another bug in the future. And so this is a direction that you can follow. And they gave examples in 2 programs for it, out of 17, which we can discuss maybe whether or not that's sufficient
But
evidence
the
for whether
zero-
this is.
Zero day,
So that's an example of, so what memset does is it takes this buffer and replaces whatever values are up there with this character which is mentioned up there. So if the buffer is say, buffer itself contains say Internet Society and the length is say 5, so it will replace the first 5 characters with 0. So I quite didn't understand this part as well. Why is that a bug?
Off by 1 errors.
Off by 1? Maybe if the input size is too large, then the buffer can be overridden by it. And that
Yeah, that's true too. That's true too.
that was a little crazy to me.
I think
I
that's
understood
because
what they were
this is
trying to
coming
say.
from an example where I guess we'd have to ask ourselves what they're trying to do with this memset buffer Sterling input. It's making some assumptions that I guess we have to hypothesize. Yeah, I guess the input could be larger than the buffer, and so they could be overwriting something with 0. And calling memset wouldn't be exploitable, this is true, because you're just initializing something to 0, so that's not exploitable. But you could overwrite something larger than that buffer. That'd be a fair explanation.
Right.
I'm not sure why you would want to do that in particular in a program. But I guess there's probably a good reason for it.
So, moving on. Later on they mentioned that to explore the loops they have. So earlier we have seen like in traditional symbolic execution, loops had this problem of path explosion. They've tried to explain how traditional symbolic executions have tried to mitigate that problem. So they limit the number of times the loops execute, and the goal is to maximize the code coverage rather than to keep on repeating those loops and check what is the effect of that particular loop on the variables which are inside. That is what loop exhaustion does up here in this technique, where it would take the loops with maximum number of iterations and would keep on running that algorithm and exploring paths inside that. But it kind of seemed a little strange because if that loop is say infinite, then what would happen? It would just come to an halt, and that is what they mention in there, that happens at a point for one of their subject programs. So to get over that, what they do is
You also have the answer on the slide. Well, a bit.
They mentioned that we use preconditioned symbolic execution along with pruning to reduce the number of interpreters. We give higher priority to only one interpreter that tries to fully exhaust the loop, while all other interpreters exploring the same loop have the lowest possible priority. So I didn't quite understand what they were trying to say.
So there are a few things, there are a few issues there. What they are addressing with that explanation isn't the infinite loop issue. So what they're addressing with that is that you could still have an exploit along those different branches. They might not be precluded by your preconditioning. The preconditioning can help prune some of the branches inside a loop, right? Because if it's mutually exclusive with your buffer size constraints, then you're just not going to consider it. But suppose they are compatible with your buffer size constraints, then every iteration from that point on, you might have to explore the paths, all those paths through one iteration and the next iteration and following iteration and so on. So they just say explore as deeply as you can and only use the deepest traversal of the loop, the maximum number of iterations that you can, as a representative for the loop as a whole. And all those previous iterations, well, you could still explore them as potentially vulnerable, but you'll put them at the lowest priority. So when you consider the fact that you could explore either branch of an if statement, one of those branches will go deeper into the loop. One of them will say, we'll explore this iteration and see what happens, or we'll exit early and see what happens. And the one which doesn't go any deeper into the loop, you will say, okay, maybe we'll consider that, but we'll make that the lowest priority thing to consider. We'll save that for later, and only consider it if our good representative couldn't find something. And in practice, they'll time out before they can actually come back to those things anyway. But that doesn't answer infinite loops.
Maybe they can use timeouts for that. That was what I was thinking.
That's the traditional way. Yeah, I mean, one way or another, they'll time out because it's an infinite state space exploration problem. So just set a maximum bound or something along those lines for an individual loop and be done with it.
So that's how they find the vulnerabilities or try to find the vulnerabilities. And now we'll see how to exploit those vulnerabilities which we have found. So it's not yet clear that what we were getting from that particular process which we saw earlier. So what we get at the end is a predicate of that particular path, and we want to get a concrete input to that particular predicate path, where that would satisfy the vulnerability, and later on we can use that information to generate an exploit, or rather point it to our shellcode. So we'll look at this predicate path up here, which we got from the previous process. And what this particular part of that predicate says is that if all those conditions are satisfied, if the input length is greater than this much and the size of this input is greater than whatever the size of the buffer is, then these locations from 0 to 63 has my shellcode, and 64 has the shellcode address. So what we are trying to define in the predicate is that this is our exploit and that is the vulnerability. So if both these conditions are true and satisfiable, then just give me give me an output, say yes, yes it is exploitable.
So what does that look like in terms of that nice little memory layout?
So I guess from 0 to 63 would be this part, which is the return address.
Start from the bottom and go up, right?
So, is this 0?
Yeah, that would be input 0.
I thought we would plan the shellcode in the return address up there.
So the way they've framed this here, the shell code is inside the buffer.
Okay.
This is the opposite of how they present it in the paper. Because their system is configurable, you can put it in either place. That buffer holds the shell code that they want to execute, and then the return address, which is input 64 through 67,
The shellcode.
holds the address of the input, which is the shell code. Right? So the bottom part of this is all filled with shell code, and the top part is the new return address that we're overwriting. So when this function returns, it'll jump to the buffer that is filled with our input, which happens to be a program. I see potential confusion, or no?
Can we like track them on the memory layout there?
Can we track?
Yeah, I mean like the control package for the bus phone that they have like in the left side. So how does it relate to the memory layout that they are showing here?
Sure. So do you want to go through that again?
Yes. So 0 to 63 is, so initially we start with an input length which was greater than IFR name. That is that. Then we check that whether it is greater than 68 bytes, because otherwise we won't be able to put in all that information which we want to later on. Like we won't be able to satisfy our attack. And then in this.
So the number 68 bytes is just the distance between the IFR name and the return address?
Yes.
So what are these telling us? Well, the first thing tells us that we're overflowing a buffer.
Yep.
And the second thing tells us we're overflowing it enough that we're overwriting a return address.
Okay. Does it have to be, I guess, any return address that we'll be returning in the near future?
Well, the first return address you hit is going to be something you jump to. So if you overwrite that with something meaningless, then your program's going to crash before you finish the next exploit. So usually it's going to be the first return address. They've got some things that can help get around that, but it's more complicated. So usually it's just the first return address.
Okay.
So then 0 to 63 is our shellcode, which is from here to here, which was the actual buffer length, which was up till here,
Yep.
which was our actual buffer length, which was allocated. And from 64 to 67 is the return address up here, which is the shellcode's address. So when this would execute, it would return the address to exactly where our program was written, the shellcode, and hence it would return the shellcode itself. And we had successfully hijacked the code. So what we do with this predicate is we give it to a solver, and the solver generates that input string, which would fit this predicate condition. So this is the whole AG algorithm, which we just saw before. So it takes the source code, and it takes the binary version of the source code, so this is the part which I did not talk about really in detail because it involves the technical implementation. So this is the binary code of that source code, and this is the LLVM representation of that code. Why we are taking both of the binary code and the LLVM code, because their justification is that either one of them, if we take only the binary code or the LLVM representation, they won't satisfy our cause because they are both good at doing different things, and we'll see how we leverage both of these files later on in the code. So we are taking the binary version of the code in the LLVM representation. When we go through the source analysis, it gives us a max value, which would be the value of our buffer overflow, or the max of like how much we can write in the memory to successfully exploit it. And this feeds it into the bug find. Bug find takes help of this max and the safety condition. So what are safety conditions are? Like say buffer overflows or string format errors. So that would be our safety conditions. So safety conditions plus this max up there.
So in terms of the previous process that we discussed, what is max?
So max would be the maximum user input plus the space which we can exploit.
Which we called,
Which
we called that something, right? Anybody? We called that something?
Yes, okay.
That's the preconditioning,
precondition.
right?
So we take, yeah, that was a precondition. So we take that precondition and the safety conditions up here, which would be buffer overflows and all those things, and generate a buggy predicate. So that's just the part which we saw in the previous slide up here, which is these two lines up there. So this is the buggy predicate up here, which we then feed into the exploit, and what we get from here, we send this buggy predicate up here. So what bug find takes is the LLVM representation, the safety condition, and the max, and it gives you back the V, which is the vulnerable function, where that vulnerability was found. So in terms of programs, you actually know that which function is buggy. Now, what the binary analysis does is digital binary analysis, dynamic binary analysis. So this is the dynamic binary analysis. What it does is it takes the binary code in and takes this buggy predicate and the vulnerable function. It generates this particular function generates a SMT solver, which we saw earlier. It generates a concrete input for that and feeds it for the buggy predicate, and it analyzes the binary code which corresponds to this vulnerable function, and it gets all the runtime information about the program. So that's why we needed the binary code initially.
What sort of runtime information do we need? Why do we need runtime information?
Because you need to know what's on the state of the system. You need to know what's on the stack, how far away your return address is.
Okay. We don't actually know where the return address is necessarily until we have a compiled version that tells us where the return address is. So these actual numbers about how big things are, where they're spaced in a stack frame, what we actually need to do to guarantee that we have something exploitable, we don't really know those until we have the binary.
So that's why we need the binary, so that so that we have the return stack variables as well. So what could also happen is that, say, there's a, look at this example up here, we'll understand clearly why we need to restore the stack and why we need the runtime information up there. So if we look up here, there's the overflow which is happening, but then at the second line, there's this pointer which is getting and if we don't restore these values properly, then we'll run into a crashing bug.
So this is an issue where we might have had something that tells us we can create a buffer overflow just like we wanted to, put our shell code into the stack buffer, but we'll crash before we exploit it.
Because we did not restore the values which were statements between the return statement and that bug properly.
Do people see why that happens?
Because we are overriding all of those.
Yeah. So the pointer PTR up there is a stack variable. And in order to overwrite the return pointer, we overwrite that stack variable as well. So this means its value is corrupted by us as a part of making our buffer overflow large enough. And so we need to give it a meaningful value, or else the program's going to crash before we do our malicious mischief.
So while we were overwriting all those memory addresses, we corrupted the values which were already on the stack. So that's why we would crash.
Could you tell me which one would crash?
So because we did not restore this value for the pointer properly.
Okay.
We overrode all that information with our shell code mischief.
So the solution there would just be to put
To
anything.
restore the stack later on.
So you can just record the values and the observed run in the dynamic binary analysis
Oh, yeah.
and just write them back in. Just copy and paste.
Okay.
Next, we generate our exploit with the runtime information. Now that we have the runtime information on all these stack addresses and all of those things, we can feed the buggy predicate and the runtime information to generate an exploit. So, which would be adding the shell code and all those things, and we get this predicate which corresponds to this last one up here, which is exactly the thing which we got from that step. And then we can just verify the bug, whether with that concrete input which was generated earlier, we can verify whether the exploit is actually existing or not. If it is not existing, like if it is not equal to null, I guess we return the exploit and then we do it iteratively again. So there are a few certain points which I think I missed up there. While we are generating exploits, it could be quite possible that the shellcode doesn't fit into our stack memory. So what do we do then? So in the paper, it's written that they have this database where you have a lot of shellcodes, different kind of shellcodes, and you can exhaustively put them in that memory space and see whether it is happening.
And you can also decide to put the shell code before or after the return pointer. Right? So that gives you some flexibility in the space.
Do you have enough for
Do we want to go through stack restoration already?
I think we talked about that. You can just overwrite things. There are some issues there. So
So some of the other challenges which they have addressed is besides precondition and path prioritization heuristic. They've dealt with format strings. They've dealt with the return to Libc, which is mentioned.
Okay.
And for reliability, so what happens in the stack overwriting? There are certain security measures which the operating system takes itself. So what it would do, it would randomize the memory locations. So you can see why that would be a problem, because if we randomize it, we might not, our return pointer might not address to the same place where we actually wanted it to, because the address space has been randomized.
Are people familiar with ASLR, or address space layout randomization, at all? So it's basically the idea that different portions of your program, say your main program, some libraries you use, etc., will just get thrown into different places in memory every time you run your program. And so this means that you can't necessarily reuse that pointer over and over. It turns out there's some patterns there, and sometimes the ASLR isn't as good as you want. So it's not a concrete defense, but.
So how do they overcome that randomization security check by the operating systems? They insert no operation sledge. I would say.
So they this doesn't necessarily actually help with ASLR. They mention ASLR as a potential barrier, but this only deals with other smaller noise. ASLR is actually a bigger problem for them that they don't really address, in my opinion. But a NOP sled is a standard exploit technique where you can have your shellcode, and maybe you don't get an exact pointer to where your shellcode is, but if you get a pointer to anything before it, and that is in some big NOP sled, then it's just, okay, this instruction does nothing, go to the next one. This instruction does nothing, go to the next one. And as long as you get a pointer anywhere in there, you'll eventually slide down to your shellcode, because all the instructions before them just say, do nothing in advance one. Standard technique.
But I thought they mentioned it as a solution to the randomization because.
Well, they mention it as a solution to robustness issues, of which ASLR is one.
So
They're careful.
in that example, you would clobber the rest of the program. Like it would become non-executable.
As long as that happens after your return,
Mhm.
you don't care.
So what does this? So this, you
That's
don't
it.
care about the exit. So what do you get out of this exploit?
Well, all you care about is returning to your code, right? If you can return to the code you want, you don't care about overriding the rest of the stuff.
So you have no. You just want access to the system.
Yeah.
And then they have mentioned that they have handled a lot of environment problems, which was not too clear to me.
Yeah, they don't really go into detail. That's standard stuff anyway. Boilerplate.
So back to the results. Analyzed 14 applications for 3 hours and generated 16 working control high-def exploits, which in detail are these. And it looks like time-wise they were doing quite okay, but they are, yeah. But they are dealing with only 2 vulnerabilities, but they are found pretty widely. So I guess
Two types.
two types, and they are found pretty widely, and that's why it's quite handy. So, in summary, what we have seen is a preconditioned symbolic execution, path priority exploration, which is first buggy loop.
Well, we have a
and-
summary.
And it does not deal with other vulnerabilities like heap-based overflows, integer overflows, timing attacks, and platform-independent exploits.
So let's talk about the prioritization for a moment, if people want to.
Yeah.
They mentioned that exploring a bug, when you've seen one bug, it makes it more likely you're going to see something later. Did they actually offer evidence for that? They said anecdotally that it occurs, they see it help twice. So that's twice out of 17 times. And that's as good as random. Maybe it was meaningful, maybe it wasn't, in my opinion. So there's some of these things where there are nice stories and there aren't necessarily justifications for them. This is not uncommon in security papers because they don't necessarily care whether their technique works all the time. If it works a small percentage of the time, yeah, then that's good enough. So they don't have to necessarily be as precise as long as they've got a compelling story.
As long as it works, that's fine, it just works.
Yeah. Anyway, I guess that's.
Are bug overflows difficult to detect? I mean,
It's not a question of whether they're difficult to detect dynamically. they're easy to observe dynamic, or they're easy to observe dynamically.
Yeah.
The question is whether you can find one without an execution that forces it to occur. And that's hard.
Okay. Alright. But is the Blue Waters does that?